This will be my video presentation for my final project for CPE 133, a temperature conversion calculator by Tom Alkayam. Moving on, what we see often in modern society is that due to having both the metric and imperial systems, unit conversions has become a significant issue within society, and as a result I felt that the best use of time and energy that I was going to put into this project was creating a logic gate based temperature conversion calculator. The implemented design that I chose for the temperature conversion calculator was to create a 6-step process that takes in an input that can be either positive or negative at an 8th bit width and convert that into its 8-bit result as a Celsius or Fahrenheit depending on your input. The way this functions is by first of all taking in an input CF, which decides whether it's a Fahrenheit to Celsius at a 0 state or a Celsius to Fahrenheit conversion at a 1 state. This data is then put through an initializer along with a neg input, which dictates whether the input value will be either positive or negative. The initializer sets up the inputs to go into the rest of the modules throughout the system. In this case, if we were doing a Fahrenheit to Celsius conversion, the initializer would send a 5 to the multiplier and a 9 to the divider as their secondary inputs, and then the process can continue. If the input is negative, then the apply -1 module will of course invert the binary value into signed binary, so that way the add and subtract module can appropriately use it. The result is then processed through the universal 7 segment that was made by Mealy, and then it is sent to the 7 segment display on the Basys 3 board. Alright, now we're going to take a look at the top level module for the temperature conversion calculator. As we can see on the bottom left, we can see the 4 primary inputs along with the 2 outputs in the figure below. What we can see is that the 8-bit input A is going to be the temperature value that will be converted. Neg is our decider whether the input is plus or minus. Enter stage 1 is what starts the process of the calculations, and CF decides whether the conversion is from Fahrenheit to Celsius or Celsius to Fahrenheit. The 2 outputs, seg, an 8-bit output, and an, a 4-bit output, are used to communicate directly with the onboard Basys 3 7-segment display. Moving on the right you can see the image of the Vivado elaborated design render. What we can see from this is initialized values start at the initializer, where MV, ASV, and DV are the deciding values sent to their respective modules, being add, subtract, multiply, and divide. They are decided by the CF value, and the neg input that goes into the initializer decides whether or not the positive to negative or pos to neg module either passes its input through to its output or simply inverts it into a signed binary value to be used by add subtract. Given these, we can see that CF and neg are able to decide which conversion process is used, but still using the same amount of modules in order to accomplish the same task. If we were to follow a specific input, for example, what would happen is first, the values are scanned, neg and CF are scanned by the initializer. Then the proper optimized inputs for the multiply, divide, and add subtract module are decided on. They are then sent to those modules, and then the calculations can start. A is first multiplied by the appropriate value. Then once the multiplying sequence is done, it is sent to the divide module. The divide module then has the input value divided, the processed input value divided. This is then passed on to the pos neg module if it needs to be flipped, or otherwise then it is sent to the add subtract module. This final output then represents the actual final converted value. It is then passed onto the universal 7-segment display processor made by Mealy, which is then processes the values to be used on the Basys 3 7-segment display. Now onto the initializer module. The initializer module is the cornerstone of the TCC's ability to be able to convert between CF and F to C temperature conversions. The reason behind this is because the initializer acts as a giant multiplexer, allowing to pick between appropriate values for the operations. The reason that the multiplexer works in this way, or can work in this way, is simply because distributing the 5/9 or 9/5 in the equations relevant to the conversions of C to F allow to make a uniform operational style, such that you can have the F value times 5 divided by 9 minus 18, or the C value to be converted times 9 divided by 5 plus 32. Following this method, you can actively decide which value goes where for the multiply, divide, and add subtract modules. The neg input is then simply used to confirm whether or not the pos to neg module has to be applied in order to appropriately apply a times -1 in order to calculate in the add subtract module the correct value. Now we cover the multiply module. This module is basically a copy of the CPE 133 Lab 6 module that we used prior, however modified to fit in the TCC. There is also some other modifications to it, such as a modification to the multiply FSM, which allows it to output a specific 1 or 0 value when it has completed the process of multiplication. The reason behind this is to allow for synchronization, and this will be discussed further on the failures section and the resulting solutions. The way that this module functions is by taking in two inputs, one 8-bit input and one 4-bit input. The 8-bit input is then put into a shift register where it is left shifted each clock rising edge about 4 times until the FSM, or the regulating state machine of the multiplier module, has gone through all of the bits of the inserted B value. The B value will of course be one of the inputs either 9 or 5 decided by the initializer module, given the CF value that we saw in the previous slide. The shift register then either is loaded to the accumulator, the value of the shift register is then loaded to accumulator given the value of B. So if a bit of B is 1, the value will be loaded to the accumulator, and then the shift register will move left. Then the next bit is checked for B, and this process continues until the accumulator is filled with all of the checked values for the bits of B. This can result in an effective means for multiplication similar to that of multiplying on paper. Now we move on to the divider module. This module is a completely custom module that I designed early on in this project, and consists of 5 submodules. The way this divider functions is using a regulating FSM known as the divider FSM that has a 3-state figure, as you can see on the bottom left. However, the sub-state is a self-repeating state as necessary. The way that this module functions is by loading value A, the value to be divided, onto a module known as a decumulator. The decumulator is essentially just an accumulator, however, instead of addition, it does subtraction. The B value is then loaded onto the secondary input of the decumulator, and what occurs is each time the clock rising edge occurs, the value of B is removed from the value loaded into the decumulator. Each time this happens as well, these values are checked by a comparator that sends a signal back to the regulating FSM. When the comparator tells the regulating FSM that the value of B is greater than the value of inside of the decumulator, then we know that the process is complete, and the output can be sent forth along with a completion signal similar to what we installed in the multiply FSM in order to allow the next stage to move synchronously. Now on to the positive to negative module. This is a very simple module that intends to convert an 8-bit input A to signed binary as an output Q, or simply pass it onto Q if the confirmation value, or conf neg, is false. This allows for a system to be used to apply a times -1 value if need be. The premise behind this module is that if I insert -18 into a calculation, I can pull off the -1 and treat the rest of the multiplication. For example, -18 times 5 over 9 can become -1 times 18 times 5 divided by 9. So by prioritizing the times 5 and divided by 9 portions first, and then applying the -1, we can have accurate binary math that allows us to then do addition and subtraction without the error that we would have gotten by attempting to do a division or multiplication operation on a signed binary value. This is the add subtract module. It is essentially a clone of the Lab 4 module used in CPE 133, except with the significant modification that it has been converted into an 8-bit width rather than a 4-bit width. As we can see, the two primary and secondary input of A and B are 8-bit width and are the values that will be added or subtracted together. The sub 1-bit input will be used to determine whether it is subtraction or addition as the operation. The output Q is the final result, and neg is the sign of the output. As we can see, it's a pretty rudimentary system using two modified RCAs containing only full adders in order to add and revert the value. We use a validity checker to confirm that the addition operation is in fact valid, as well as muxes two muxes throughout the system in order to A, determine how the operation will proceed with addition or subtraction, and B, determine whether the output Q is already positive or needs to be use the flipped version in order to show the correct value. The output of Q and neg represent the final converted value once all other values have been put through the system and eventually entered the add subtract module. These 8-bit, the Q 8-bit value and the neg 1-bit value will be sent to the universal 7-segment processor made by Mealy in order to be displayed on the Basys 3 board. Now before we finish, I'd like to go over the successes that I achieved during the TCC project. In this case, one of the most significant ones was the independent functionality of all submodules prior to the top-level module. In this case, the multiply, divide, add, subtract, positive to negative, and initializer modules all worked independently of each other prior to being compiled together. As a result, this made work significantly easier on the project, and the reason behind their functionality prior to installment was due to vigorous testing beforehand. Use of Vivado simulations to ensure proper expected values allowed me to create all 5 modules to spec and ensure that they functioned well. Another valuable success that I achieved during the TCC project was the utilization of a particular mindset following a flowchart to create the modules and the synchronization of the modules. This flowchart can be seen in slide 3, and using that as direction, I was able to create a synchronous system that allowed me to operate both from Celsius to Fahrenheit conversion and Fahrenheit to Celsius conversion. This allowed me to create an effective method, saving me numerous modules and creating a more efficient system for my temperature conversion calculator. Now we move on to failures and the resulting solutions from those failures. The most difficult issue that I encountered while creating the TCC was proper synchronization of the multiply and divide modules. My biggest issue with those was that I could not properly synchronize the end of one with the start of the other initially. I attempted to use continuous assignment to solve that issue, but however, not only did it not work, it was also rejected by the Vivado synthesis function, making it utterly useless. To that extent, I had to find a system that already existed within those modules or create 2 new modules within those systems that could operate on a synchronous clock and knew what state each one was at. It's funny because those modules were already there, present as the FSM modules. It was quite the inspiration when I realized I could simply add a end feature or an end output to each module and convert their original enter values to attach to those. As a result, the first enter that enters the TCC activates the multiply. When the multiply module is done, it outputs a end value, which becomes the enter of the divide module. As a result, I was able to effectively synchronize them and was able to learn a new skill to apply in future projects. Another minor issue that occurred during my construction of the TCC was when working with the pos to neg. Initially, I had it at the start of the TCC top level module, intending it to apply the negative first and then run with the multiply and divide throughout. However, that resulted in significant error because a signed binary value cannot undergo the same math and expect the same result as a normal unsigned binary value. As a result, I used order of operations and the same precedence of multiplication and division to move the -1 to the end of the multiplication division function, and as a result, you convert the final multiplied and divided value for the temperature conversion by -1, and then take that into the add subtract module, which could handle the signed binary value. This allowed me to think ahead and realize that you can utilize different methods of thinking to solve your problems without actually having the code to brute force it. Finally, one of the issues that I could not necessarily solve, but I was able to benefit off of, was the 8-bit width limiting the amount of inputs I could enter. Because I chose to multiply, then divide, what occurred is I reached the 8-bit limit really quickly. I initially thought that I could divide first, then multiply, which would open up my input width significantly in the amount of inputs I could take. However, by dividing first, the loss of values due to the round down of the divider module would propagate throughout the whole rest of the TCC project, and as a result, this would result in a lot more error. Hence, in my opinion, I felt it was best to proceed with the TCC with a smaller input range, but a more accurate ability to output a converted value. This limited the conversion values from -50 to 50 for Fahrenheit to Celsius, and -28 to 28 for Celsius to Fahrenheit. As a result, we can see that the windows are not necessarily the largest. However, I can guarantee significantly more accuracy from these windows than if I were to use, say, a divide operation and then a multiply operation. This concludes the presentation portion of my video.
Alright, this is the CPE Lab Final project demo. So, starting from the top, we'll test the zeros from Fahrenheit to Celsius conversion, Celsius to Fahrenheit. Right now we're in Fahrenheit to Celsius, as can be seen by the leftmost switch. This switch indicates the negative, if the input value will be negative, and the 8 most switches from the right indicate your input value for temperature. So let's start it off. As we can see, 0 degrees Fahrenheit goes to -18 degrees Celsius. I've pulled up the Google converter equivalent to also show that. As we can see, we can't account for the decimal points due to the divider being only integer only. Hence, we only get -18. Let's move on to Celsius to Fahrenheit. So 0 Celsius goes to 32 Fahrenheit. As we can see, that corresponds to both what we expect and what the Google conversion calculator shows us. Let's move on to some more basic examples. For example, 15 in Fahrenheit to Celsius gives us -10 Celsius. When we plug that into the conversion calculator, we get -9.444. As we can see, it's within the expected error range and on target. Moving on, let's say we transfer this to Celsius, so 15 degrees Celsius to Fahrenheit. We get 59 on the Basys 3 conversion calculator I have made, and we get 59 on the Google results. When we move on to -15 Fahrenheit to Celsius, we get -26 degrees Celsius. And the Google conversion calculator spits out minus 26.111. As we can see, we're within the expected value range. Now let's push it to the extremes. For example, 51, which is the max input value that this calculator can take from Fahrenheit to Celsius due to the 8-bit width. First we input it, 110011. That should give us 51. When we do 51 Fahrenheit to Celsius, we get 10.5556. On the case of my board, we can only get 10. For the Celsius to Fahrenheit conversion, the maximum value and minimum value is plus or minus 28. So let's do the maximum value for the Celsius to Fahrenheit. First of all, we switch it to Celsius to Fahrenheit, and we put in 28, which is 00111. We got 82. The Google conversion calculator shows 82.4. As you can see, this is a fully functional calculator and follows all expected results within the error range that is given.